It is time for us to get started. This is the 9th lecture for this class. And I want to pick up where we left off. I know everybody's anxious to get their homework one back, and so I'm going to make you wait. And so that's what's going to happen. And then we'll talk about the last 5 minutes of class or something like that. I'll talk about the homework, okay? But in the meantime, let's go ahead and pick up where we left off. And first of all, let us recall from last time, we had the following facts. So here's one. One fact is if t was greater than 0, then there exists an n element of the natural numbers such that 1 over n was less than t. That was the fact that we had. Okay? So something that I'm just stating and review. 2, another fact that we had was if y were greater than 0, then there exists an n element of natural numbers such that n minus 1 is less than or equal to y, which is less than n. Okay, so those were 2 facts that we had. And thirdly, we had a definition. So that was a fact. Let me write that down, it's fact. And the third one was a definition we ended class with, and it had to do with what it meant for a set to be dense. Okay, Megan was talking to me about that before class. And so, recall, given a set script S is a subset of R, then script S is dense in R. It's said to be dense in R. If for any 2 distinct real numbers say x sub 1 and y, or x and y. Get out of the way, give everybody a chance to write it down. Look, when we say we got 2 distinct real numbers, x and y, they're not the same numbers. If they're not the same numbers, one of them is bigger. And it doesn't matter which one's bigger, we got one that's bigger. Okay? So, symbolically, I'll say with x less than y. Then, there exists an element of script S such that x is less than s, less than y. What this means is, for a set S to be dense in R, is that no matter what 2 real numbers you give me that aren't the same, no matter what 2 real numbers you give me, so no matter, if you think of the real line, no matter what little segment of the real line you're looking at, from x to y, there's something from S in between it. Okay? No matter where you are in the real line. Real close together, there's still something from S there. Is that okay? That's what it means to be dense. They're everywhere. And that's from S, they're everywhere. A fourth thing that I want to recall from a long time ago is this. The rational numbers is a set we denote by Q. And it's equal to the set of A over B such that A and B are integers, so plus or minus whole numbers, with B being different from zeros. Okay, so that's what I wanted to review. And then new. So the new thing is, I want to talk about is a fact called the density theorem. So this is a named fact. Dalvin, why it's something that's noteworthy to say it's a named fact? Now listen why it's noteworthy, is that on the test I could say, state and prove the density theorem. Because I don't tell you what it is, because it got a name. Does that make sense? That's why it's kind of something to keep in mind for tests. Like if I were to ask you, what is the order property on R? That's the thing that defines the positive numbers. And I could just ask you on a test, and that's a really fair game, to say, state the order property. Does that make sense? So for exams here, I'm going to ask you to do some computations, to reproduce proofs that we've done, maybe to do a proof that we haven't done before, but it's similar to things that we have done in class. And also to state things, okay, that's kind of important. It's saying, I know what this course material is. You've told us this fact. Here it is, I can tell you. Here's the density theorem. It says, the set of rational numbers is dense in R. Okay, so that's the state. We want to prove that. And we're going to use some of these facts that I'm erasing right now, but I reminded you of as we started. So here's the proof. Okay, how am I going to show that the set of rational numbers are dense in R? Well, what does it mean to be dense in R? It means anytime you give me any two real numbers, I can find a rational number in between them. Okay? We're not going to say, oh, look at 1 and 2, find a rational between them. What we're going to do is say, give me any two arbitrary real numbers that aren't the same, find a rational number between them. Great. Okay? So here, let x and y be elements of real numbers with, so they're not the same, I'm going to say if x being less than y. We must show there exists a rational number, which I'm going to call R. An R element of Q such that x is less than R is less than y. So that's my R is representing my rational number. That's what I got to show. That there exists. I got to create it. And the way I'm going to do it, Megan, is I'm going to break this proof up to cases based on what x is. So I'm going to do this, Chuck, based on what x is. So case 1, let's suppose x is greater than 0. Okay, so Brad, I got x and y. X is bigger than 0. X is the smallest number, so that means y has to be greater than 0. Okay? So in this case, we have 0 is less than x is less than y. Okay. Well, since x is less than y, well, wait a minute. Let's go back, John, to the definition of less than. What does it mean for x to be less than y?
Y minus x is an element of the positive.
Y minus x is a positive number. That's right. So, Audra, if y minus x is positive, that means that y minus x is greater than what number? Yeah. That's right. Okay, that's what we're on. Chuck, we're going to go back to something that we had written to start with. And that is, if you give me a positive number, anytime you give me a positive number, there is a natural number such that 1 over that natural number is sandwiched in between 0 and that positive number. So by a previous fact, I wrote it on the board today. There exists n on the natural numbers such that 1 over n is less than y minus x. And of course, this is bigger than 0. I'm not so much interested in that part, but I'll write it down. Thus, if we multiply both sides of that right-hand side of the inequality by n, we get 1 is less than ny minus nx. So I'm skipping a few steps. We're getting a little bit more mature. I don't have to write through every algebraic property of R to get that result. Distributive property. There we go. That's what it is.
okay on a test for us to skip those same steps?
Yes, I think so. This is the first assignment. I wanted you to write down something more than maybe than what people did. And even if I answered earlier that it was sufficient, I made comments to all include these steps, okay, on your homework. So anyway, you'll see them soon enough. So that's where we are. So this says that if I add nx to both sides, that 1 plus nx is going to be less than n times y. Now consider nx. Okay. That's a number. N times x is a number. We said x was what kind of number? Positive in this case. And n is positive. So you take two positive numbers and multiply them together. What do you know of? So that means it's greater than? Okay, that's right. Dalvin, there was a previous fact that if you give me a positive number, I wrote it up today, that there's some natural number, okay, that is just barely bigger than it, such that 1 minus that natural number is less than or equal to the given positive number. So by a previous fact, here's what I can say to each other. I wrote it down on the board today. There exists an m, element of the natural number, such that m minus 1 is less than or equal to nx, which is less than m. Okay? That's by a previous fact we had today. I recalled it today anyway. So what this says is that m is going to be less than nx plus 1, which is going to be less than m, less than or equal to. And that, I wrote down that nx plus 1 so we can compare it here. Okay? And I didn't write down the right thing here. What should I have written?
Plus 1.
Plus 1, that's right. Okay. Let's concentrate on m for a second. Let's concentrate on that for a second. So here, I have m is less than, let's say, nx, which is less than nx plus 1, which is less than n times y. That's what I can write. Let me put down thus in front of me. We're writing sentences here, so that's kind of a word that connects the last line I just wrote to the previous line. Or previous lines to the line I just wrote. And so, getting some of the periphery stuff out of the way, just a second. Okay, but that's this is not exactly all that I wanted. Okay? I made a mistake here. So here's what I want. Let's concentrate on. I want to take that back. So you take it back too. I want to look at nx. Okay. So nx right here is less than m. I messed up. Nx is less than m. Is that okay with everybody? Nx is less than m. But that's less than or equal to nx plus 1, which is less than ny. That's what I wanted to write. So here's where I'm looking. This guy is less than this. That was less than or equal to nx plus 1, which is less than n sub y. That's a true statement. I'm stringing together inequalities that we have there. This means then that n times x is less than m, but is less than ny. So I'm throwing this part away. I'm just saying, hey, that is something that is true, but I don't want to have it there in the way to consider it. I just want to look at this guy's less than this guy, which is less than that guy. Now remember, I'm going to work between x and y. So to get x and y in the inequalities, what should I do to both sides?
Divide by n.
Yeah, so that's the same thing as multiplying by 1 over n, which we can do, because n's a natural number. So that means that x is less than m over n, which is less than y. Okay. Now what is m? It was a... What's m? I know it has... Well, the first thing, what kind of number is it? Natural number. What about n?
It's also a natural number.
Okay, so m over n are a division between two natural numbers. That makes it a division between two integers. So that makes m over n equal to, m over n be what kind of number? Rational. That's right. So we have created, have found a rational number m over n, and I'm going to call that r, between x and y. So in this case, I produced what I wanted to. Is that okay with everybody? What case was this? This was the case where x was bigger than 0. Okay, now let's look at the next case. So case 2, okay, so case 1 was where x was bigger than 0. X is a real number, so it's got 3 options. It's got 3 options by really the order property on R, which says if you give me a real number, then that number is either positive, which means greater than 0, or it is 0, or minus x is positive, which means x is less than 0. So here case 2 is going to be x is going to be greater than 0.
We did greater than 0.
Oh, equal to 0. Yes, thank you for looking at me. Everybody looked at me kind of awkwardly, like, what are you talking about? Which, let me tell you, to be right. Then we have, well, we have x is less than y, so we have 0 is less than y. By a previous result, there exists an n element of natural numbers such that 1 over n is sandwiched in between 0, but less than this positive number y. 1 is an integer. N is a natural number, so it is an integer. 1 over an integer is a rational number. So integer over integer is a rational number. Thus, we have produced a rational number r equal to 1 over n that is between x and y. So that's case 2. What's case 3? Well, this time x is going to be less than 0. Okay. So x is less than 0. So we have some kind of subcases here. So subcase 1. Let's say y is greater than 0. Then we have x is less than 0, which is less than y. Note, 0 is a rational number. How come it's a rational number? Well, it's equal to an integer, 0, over an integer, 1. So there is a rational number between x and y in this subcase. Subcase 2. Let's say we're talking about y. What if y is equal to 0? Then we have x is less than 0. Okay, this is y. So, if you will, that means that 0 is less than minus x. Okay. Now, what I want you to recognize is this is essentially case 2. In here, we have one number 0, the other number is bigger than it. Is that okay? Can I fit a rational number in between 0 and minus x? Yes, by case 2. Not subcase 2. By case 2, there exists a rational number, so R element of Q, such that 0 is less than R is less than minus x. But I want to get something between x and y. Right now, I have something in between minus y and minus x. So if I'm multiplying everything by minus 1, so what I get is x is less than minus r, which is less than 0. This is playing the role of y. Now, since r is an element of Q, you know what that means? It means it looks like an integer over an integer. So what's minus r? It's minus that first integer, top integer, over the same bottom integer. Is that okay with everybody? So that says that minus r is an element of Q. Thus, we have produced a rational number. Here's minus r. Between x and y. We got one more subcase. That last subcase is, remember x is less than 0 here in this case. So subcase 3 is x, we're talking about y. Y is less than 0. So we have x is less than y is less than 0. We want to get a rational number between these. Well, what that gives us, if I multiply everything by minus 1, what I get is 0 is less than minus y is less than minus x. Melissa, what we're looking at is having two real numbers, both of them bigger than 0. And can I produce a rational number in between these two positive numbers? The answer is yes. Why? Anybody tell me?
Case 1.
That's what case 1 said. Case 1 was the case where we had two positive numbers. Is that okay? So by case 1, that's right, John. There exists a rational number such that minus y is less than r is less than minus x. But I don't want a rational number between minus y and x, or minus x. I want a rational number in between x and y. So what should I do to both sides of this inequality, or all parts of this inequality?
Multiply by minus 1.
That's right. When I multiply by minus 1, here's what I get. I get x is less than minus r, which is less than y. And since r is an element of Q, then what can we say about minus r? Well, it's a rational number. Thus, in all possible cases, there exists an R element of Q in between X in Y. That means Q is dense in R. And that's what I wanted to show you. That's what I wanted to show. That is the proof of the density theorem. I didn't do it exactly like the book did it. I did it similarly. But what I did was I broke it down into cases. It just had one case. And I'm not sure their proof is as accurate as it should be. Because their work, really, for case one for us, has a part in it that they're not being careful with. And that part is that they use a fact, but they don't know that n times x is necessarily greater than 0, and they need to have that fact. So I think their proof needs a little bit of adjustment. Anyway, that's what I got for you. That's the density theorem. You know, as I race the board here, I want to tell you, for me, when I first took the class, I thought the material was difficult. I still think the material is not easy. Okay? It's hard to follow all the intricacies, what's been said, how we can use that. But it's like, the course to me now is like a story. We talk about objects, we talk about characteristics of those objects, and we say, well, what do we expect to happen with those objects with these characteristics? What can we say about it? Okay? You know, if you have a person, you say that person is lustful for money. And somebody left a $10 bill on the table, and they saw it, and nobody else is in the room. You expect them to pick it up. Does that make sense? And that's kind of what I think of for this mathematical course. These things, these objects that we're talking about have characteristics. And we're just going to say, hey, well, when you get in this situation, that's what this object's going to do. Okay? That's the facts that we're going to come up with. So it's like a story. We should be able to say, oh, well, this happened, and then this happened, and then, oh, yeah, it made sense. And that's what the proofs are. They're things that make sense, that are just logical consequences of facts that we have about objects. Well, the next thing I want to talk about are intervals. So classification of intervals. And so here for intervals, let's recall what we mean by intervals. By an interval, we mean a connected collection of real numbers. Okay, so I'm going to classify them based on them being bounded or not. Okay. So first of all, I'm going to have bounded. Okay, so the first type of bounded interval I'm going to write down is this. I'm going to have from A to B. Now, A to B, this means, this interval with these brackets around it, means it stands for the set of all x values, element of R, such that A is less than or equal to X is less than or equal to B. So these are all the numbers between A and B, including A and including B. That's what that means. Okay? Is a closed bounded interval. Closed bounded interval. And what we mean by that is that out of all the points in the connectedness it could contain, it contains them all, okay? Including the endpoints. It contains all the possible endpoints that it could contain. 2, I'm going to look at A to B with parentheses about it. What does this define to be? It's the set of all x's element of R, such that A is less than X is less than B. Now this is an open bounded interval. Okay, so it's bounded because it has an upper bound and has a lower bound. It's open because of the endpoints that it could contain, A and B. It doesn't contain any of them. Is that okay? That's what we mean by open. It doesn't contain any in this sense for an interval. Well, there's another. Okay, so of the bounded intervals, the third type, if you will, looks like this. That equals to the set of all x's, that's a beautiful bracket, element bar, such that x is an element, such that A is less than or equal to X is less than B. Oh yeah. Or, part B, here I'll write down A to B in this fashion, which equals to the set of all x's in R, such that A is less than X is less than or equal to B. And so in this case, they're bounded intervals. They have upper bounds of A, they have lower bounds of A and upper bounds of B. That's what we have. So they're both bounded, and these are called half open, or sometimes they're called half closed intervals. Intervals. So what we mean by that, they contain half of the endpoints that they can contain. And they exclude half the endpoints that they exclude. Remember, the openness means we throw away all the endpoints for an interval. The closedness means we contain all the endpoints. Is that okay with everybody? Before I get to unbounded intervals, let's make some notational remarks. First notation remark I'm going to make is this symbol right here. I'm sure everybody's familiar with it. Infinity, not a bar. Infinity card doesn't spell it like that either. This means going on in a positive direction. It's not a number. It means going on in a positive direction without bounds. Well, if we have positive infinity, we ought to have minus infinity. That's right. This means going on in a negative direction without bounds. Okay, so that's what it means. And so now we want to talk about unbounded intervals. first type of unbounded intervals that I'm going to list, part A, is a to infinity in this form, or part B, minus infinity up to b in this form. You might remember about forms of infinity in interval notation, we always put parentheses, meaning that we don't get there. It's not a number. Okay? We don't get there. These are closed, unbounded intervals. Wow. Closed, unbounded intervals. So they're unbounded for part A because it's not bounded above. There is no number that's bigger than everything in the set. And for part B, it's unbounded because it's not bounded below. Why are they both closed? Well, out of the endpoints that they can't contain infinity or minus. Out of the ones they can contain, A or B, both times they do contain those endpoints. Is that okay? That's what we're closed. And I didn't write down what they were equal to. So what is this? It's the set of all x's element of R, such that what? Such that A is less than or equal to x. And this guy right here is the set of all x's element of R, such that x is less than or equal to B. Is that okay with everybody? Bounded intervals. 2. Sorry about that. The next two types I'm going to look at are open unbounded. So we could have A to infinity, which of course looks like all the x's in R, such that A is less than x. And B, we could have from minus infinity up to B, with parentheses about both, which equals to the set of all x's in R, such that x is less than b. And these guys are open, unbounded intervals. All right, they're unbounded again because we have these forms of infinity or minus infinity with them. They're open because out of all the inputs they can contain, A or B, they contain none. Is that okay with everybody? Well, there's one more. Unbounded interval. Chuck, I like making comedy. I like saying things that are halfway funny, or if they're funny to me. And I can enjoy it when somebody else says something funny. I do. So I like comedies. My wife doesn't like comedies. I don't know why. She doesn't. She can't stand the laugh tracks in comedies. I was watching this old episode of Taxi. It was a show that was in the late 70s, early 80s. You can watch them on YouTube, so I do. I won't get back to what you just said. And one of the characters on the taxi is a boxer. He drives a taxi cab, and he's also a boxer. And he's getting a chance in one of these episodes to fight a retired person who's coming out of retirement that was a great fighter. He was like one of his idols, and he's like, well, I'm so happy to get a chance to fight this guy, but I'm also very nervous. It's one of my idols, and he's a little bit over the hill. I don't know how this is going to go. I'm not a good boxer. I don't know what's going to happen here. And it turns out that the idol has a press conference. And he says he's coming out of retirement because, well, he misses the excitement of boxing. And plus, he met someone, a little child, who is, he's gone to visit in the hospital who needs surgery. And he's dedicated as an inspiration to the fight to this little child. Well, here's the other boxer, the main character, one of the main characters on Taxi. And he's thinking, I am the villain. Everybody's pulling against me. So it's a great setup for comedy. Here's one of the main characters you're going to pull for him. And he's like, I'm even pulling against myself. I don't even want myself to win because I want, the little kid's fighter to win. That type of thing. That's kind of funny. I enjoy that about comedy. Well, I'm about to do something I think that's comical. And I don't have anything to do with it, Melissa. It's the mathematical words. I just find them maybe comical. We got one more unbounded set to talk about for an integral. Can you guess what it is? Okay, so we can't include forms of infinity, so we'll put this down. Okay, what is this equal to? This equals to the set of all x's in R. That's it. It's equal to R. Okay, that's not the complicated part. The question is whether it's an open set or a closed set. So does it contain all the endpoints? And does it exclude all the endpoints that it can? Does it contain all the endpoints that it can contain? Yes. Does it exclude all the endpoints that it can?
Yes.
Yes. Okay, so that means it's both open and this set is open, is an unbounded set that is both open and closed. Okay, here it comes. It's called a clopen set. Now you think I'm making it up, I'm not. That's the mathematical term. Okay? It's called a clopen set. Yeah, go ahead. Anyway, that's what it is. All right. That ends the most basic of material of the course, having to do with real numbers. And what I want to do now is give you one more definition, and then we're going to get to homework, I guess. One more kind of topic, and we're going to get the homework out and talk about it for a second. It is funny, right? Clopen. It's clopen. Man, that's clopen. Okay. So, a definition. A function, this is the pre-calculus definition, is a mapping or rule of correspondence in which each object in the first one is associated to exactly one object in the second question. That's what we say in pre-calculus. That's the correct definition. Give everybody a second to write that down. And then I'm going to write down the way we will define a function. And you may have seen this definition in previous class. Let me write this down. A function is a set F of ordered pairs F is equal to the set of A, B, such that if AB1 and AB2 are NF, then B1 had to be equal to B2. And we think of this as A is associated to B. First coordinate's associated to second coordinate. So if AB1 and AB2 are now, that means A goes to B1 and A goes to B2. To be a function, B1 had to be equal to B2, because A can't be sent to more than one thing. It has to be sent to exactly one thing. Is that okay? Okay, so that's the definition. We'll talk about that a little bit more next time. That's going to conclude the lecture. I want to spend just a minute or two passing out your homeworks and talking about it. First of all, the scores were not beautiful. They weren't. Okay. There's some improvements to be made, and I wrote down what could be done. But the other thing I want to tell you is that you have a chance to do improvement. And if you don't know what I'm talking about, my handwriting's real small and messy, then you ask me, what are you looking for here? Okay? So this is where you come by and see me and say, I don't know what it is I should be doing. Okay. So Mary's not here. Corey's not here. Melissa's here. Audra's here. Now remember, we won't get a chance to improve these scores. This is what you got so far. And your score can't go down from here. Okay. Next submission. The next thing you do is you rewrite it with problems that you missed something on that you want to get some more points for. You rewrite those problems, submit them to me along with the original submission so I know how to grade it. Chuck, here's yours. Mariah's not here. Dalvin is here. Megan is here. And sometimes I was real picky because in this first homework assignment, I wanted to say, let us follow everything exactly step by step. So some of you thought of things in very innovative ways, different than what I did, and that's great. There were some proofs I said, that isn't the way I would do it, but that is correct. So that did happen on homework submissions, and I was happy for that. But if you have questions about the way that I graded something, you let me know. You want to know what is it that you're thinking about? What was wrong with this? I'm going to tell you. The most common mistake that I saw was on occasion we were trying to prove equality statements quite often, and sometimes people would kind of assume the statement we were trying to prove. They said, well, if this is true, then we can do this, we can do this, we can do this. We don't know it's true. That's what we're trying to prove. So that was a mistake that several people made in their submissions at home. Don't forget, you know what each part is worth, or each problem is worth. So you can see what I graded it out of. If you have questions, you just let me know. Okay? All right, that's what I have for you. I'm going to shut off I'm not going to shut off. Does anybody want to ask me something right now? Is there a problem? You said, what the heck? What did you want here? That's okay to ask.
Now, there's such a thing as stating what you
want to prove. Yes.
And then finding something that is true from it. Is that a type of proof?
Well, you start off with a direct proof is where you start off with the assumption of the given conditions, and then you work your way towards the conclusion. Okay? So that is a direct proof. Are you asking about a specific part? You can ask something you want.
I was one of those people who made a mistake of assuming.
Audrey, why don't let's take a look at one of them. Which one of them do you want to look? Let's look at one specific. I'd like to give everybody a problem. Do it.
Sure, 1C.
1C, what's it say?
It says that quantity negative 1 times A is equal to negative A.
Okay, so show negative 1 times A equals to. That's what we'll show. And let's recall, we have already proven some things. Okay? So one thing that we've already proven is, we've proven if A plus B equals to A to 0, then B equals to, okay, that's what we proved. So first plus second equals 0, the second equals to the additive inverse of the first. All right, here's what I want you to know. So I'm not going to start off with either one this time. This time I'm going to say something I know to be true. I know that 0 times A equals, this is something we proved. 0 times A equals to? Be careful. 0. I'm going to rewrite 0 times A as something that involves minus 1. Okay? Is that okay? So that means that 0 is the same thing as 1 plus minus 1 times A equals to 0. Now, working with the distributive property, this would say 1 times A plus minus 1 times A equals to 0. Is that okay? Now, Chuck, I'm in perfect position to use this part 1A of the problem set. Audra, If you have first plus second equals 0, that means second's equal to minus the first. Here I have, well, maybe I should write one more thing. Thus, before I get myself in that position, what's 1 times A, Aldrin? A. So I got A plus minus 1 times A equals to 0. Okay. Using property 1A. First plus second, look at me, Aldrin. First plus second equals to 0. That means second equals to minus, and in this case, minus the first is minus. And that's what I wanted to show. I'm done. So that's by 1A. And look, it takes time to notice these types of things. So I'm giving you one now. Is that okay? Because we need somebody to help us every once in a while. That's what I think I did. Anyway, if you're wondering, well, what was I supposed to do? You come by and see me, okay? I'll tell you, here's what you're supposed to do. Look, I'd like for you to turn in on Wednesday, okay, the redos. And I think on Wednesday I'm going to give you another homework set to do in a week after that, okay? And you'll have to do, I think that's what I'll do. I'll look. But that could happen, okay? Thank you very much for your time and patience. Don't forget